Artificial Intelligence Doctor. User question. How does the chronic presence of a leadless pacemaker within the cardiac tissue influence local and systemic neural pathways over time? Gemini Advanced answer. The chronic presence of a leadless pacemaker within the cardiac tissue can induce a variety of changes in both local and systemic neural pathways over time. These changes are complex and likely involve a combination of mechanical, electrical, and potentially even biochemical signaling. Here's a breakdown of potential influences. Local neural remodeling. The physical presence of the device can cause microdamage and inflammation in the surrounding cardiac tissue. This can directly affect local nerve endings, potentially leading to denervation, loss of nerve supply, or altered nerve fiber density in the immediate vicinity of the pacemaker. Over time, this could result in changes in local reflex arcs and sensory feedback from the heart. Mechanosensory adaptation. Cardiac tissue is rich in mechanoreceptors that respond to stretch and pressure. The continuous mechanical stimulation from the pacemaker's presence and its subtle movements with each heartbeat could lead to adaptation or altered sensitivity of these mechanoreceptors. This could affect the afferent signals sent to the central nervous system regarding cardiac activity. Altered electrical signaling. The consistent electrical impulses delivered by the pacemaker can influence the electrical activity of nearby nerve fibers. This chronic stimulation might lead to changes in neuronal excitability, firing patterns, or even the expression of ion channels in local neurons. Systemic autonomic nervous system adjustment. The altered local neural signaling from the heart, due to the pacemaker, can be relayed to the central nervous system, potentially influencing the overall balance of the autonomic nervous system, sympathetic and parasympathetic activity. The body might adapt to the consistently paced rhythm, leading to adjustments in baroreceptor reflexes and other regulatory mechanisms. Neuroplasticity in central pathways. Long-term changes in afferent signaling from the heart can potentially induce neuroplastic changes in the brainstem and higher autonomic centers. This could manifest as altered perception of bodily sensations, interoception, related to cardiac function, or changes in the central regulation of heart rate and blood pressure. Potential for adverse neural effects. While the pacemaker is designed to be beneficial, chronic irritation or inflammation could potentially contribute to the development of pain or discomfort mediated by local sensory nerves. The long-term impact on the delicate balance of cardiac reflexes also warrants investigation. Influence of pacing mode and rate. The specific way the pacemaker stimulates the heart, e.g., fixed rate versus demand pacing, and the programmed heart rate could differentially influence neural pathways. For example, a consistently high pacing rate might lead to different adaptations compared to a rate that adjusts to the patient's activity level. Understanding these long-term neurophysiological adaptations is crucial for optimizing leadless pacemaker therapy, predicting potential complications, and developing strategies to enhance the physiological integration of these devices.